Oh, I'm sorry. And they're like, oh shit, oh, it's the sound settings. And you're like, I screwed you over. Not that I do that. No, 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 I never do that. Right, here we go. Доброе утро. Как дела? Хорошо? Все хорошо? Все хорошо. Yeah. Who am I? I have been, as Alex has said, I have been here a few times before, pretty much every RSConf here. Who has been at the first RSConf here? Keep your hands up if you have also been to the second. To the third. Trick question. This is the third. So if you're not raising your hand, you're not listening to me. Stop checking emails. Or Twitter or whatever. You know, you have a coffee break. I am the lead engineer at Archeologic, which is a small company in Zurich. We do this weird WebGL things, which are pretty funny. We break stuff on the web all the time because we are, experimenting on the edge. I have contributed to a few W3C specs. I am a Google Developer Expert for web technologies, and I am a Mozillian as well. So basically, I have browser nonchalance, browser casualness, right? This is a Firefox OS t-shirt. We all know Firefox OS, the most important and successful mobile operating system of the world. Yeah, it really is. I really like it. It's dead, but it was nice. You sometimes see me in Edge t-shirts as well. I actually have an Internet Explorer t-shirt, and the best thing is it says I have standards, and it's just so sassy. It's hilarious, isn't it? Anyway, moving swiftly on. What I'm here for is I want to talk to you about things that are not very common, and I think it's interesting to have a look at and think about them, because you might encounter problems where you might want to use one of these technologies. We're going to talk today about how you can get your JavaScript to do things that take a lot of time, and it's relatively expensive, computationally expensive, because have you ever seen this page does not respond, or the JavaScript on this page does not respond pop-up. Browsers every now and then do that, and you're like, yeah. And then it crashes, and you're like, no. How do we avoid that? Well, there's a couple of techniques that we're going to talk about today. We're going to see basically in a sample application how we can do edge detection. So basically, we want to find edges in an image using JavaScript. And there's a lot of people from other language worlds that go like, you can't do that in JavaScript because JavaScript is a toy language. You're wrong. You can do this in JavaScript. It's just a little tricky to get it right maybe. Actually, it's not very tricky. And then we're gonna see how we can use web workers, GPU, so WebGL basically, GPU computing, and WebAssembly to solve the same problem. WebAssembly is a bit of a experimental thing yet, so unfortunately my tool chain has crashed yesterday, so I can't really demo that, but well, there we go. So let's start with the problem, right? Let's start posing the problem. So we have an image, and in this image we want to find the edges, right? So basically we turn this kind of wonderful colorful image, that's actually the GUM in Moscow during Christmas season, as you can tell, because that's totally Christmas, everything sparkles. And we want to find all the edges. All the bits and pieces should be white, where we have some sort of edge, really. This is a weird one. This is full of edges because it has these little lights. And each light has an edge, right? It has a sort of shape. That's why this is very, very white. But, well, there we go. And the first thing you might want to do is you might just want to program that in JavaScript, and then you run it on the main thread. And this is what you get. So here we see that we have, it's a little small, but don't worry, it doesn't matter too much. Here you see that basically this is where the image loading happens, and then this is where the actual kind of JavaScript starts executing. And then we have this gigantic block that says edge detection. And that's the code that we run to detect the edge in this image. And that's 2,600 milliseconds. Now, how many frames per second is that? 0. Amazing, right? Which means that, and this is going to be fun because I now have to navigate to the other tab from here. Yeah, that's going to be great. So here we have this wonderful application. It loads this gigantic image. The image is actually 4,000 by 4,000 pixels. And we have a slider that allows us to say how much of an edge a pixel has to be to become white, and we can change the slider. So for instance, I could click here. Oh, is it broken? No, it's just very slow. Right? Because we are blocking the main thread, so I can click all I want. I can click here, and then later I can click here, and it doesn't really, that doesn't feel great, does it? And obviously the people go like, I told you JavaScript can't do that. Silly, silly man. Why would you do this? You're a weirdo, man. Just use C++, really. Where did my clicker go? Ah. The world of 3D, where things can obtrude other things. This is what happens. So the code takes that long because it does a lot of operations. And basically what we do is, we take every pixel in the original image, we look at the 6 neighboring pixels around it, depending on if you want to find vertical edges or horizontal edges. You look either at the 6 pixels around them vertically or around them horizontally. Sorry, actually that way around, or that, anyway. You look around the pixels around them, you multiply them with a certain weight, and this is called the Sobel operator. This is for vertical edges, this is for horizontal edges. And you operate this. So basically, if we have 4,000 by 4,000 pixels, we have to do for every single pixel, we have to look at 6 other pixels, and then we have to do these operations, and then afterwards we have to also, because we want to have any edge, really, right? So we basically, instead of just taking one of these two, we actually do both of them, and then we square them, then we add them together, and then we take the root of that, and then we know if it's an edge or not, and then we compare against the threshold. The threshold is basically the value, how much of an edge it has to be white on the screen. And we do this over and over and over and over again, so it's a lot of operations. Now, as you might have heard, JavaScript is single-threaded. And what you might not know is that everything that happens in the UI is on the same freaking thread. So all these operations that we run basically make the browser go, I'm very busy right now, I can't. And then you click, and then the browser goes, hey, handle click, and the browser goes, I can't, I have to execute this JavaScript, god damn it. Just wait, okay? And then it does its thing, and then it goes, okay, so what was that? Oh, right, a click, yeah, there you go. So that's not very nice, right? That's what we have seen. We click on something, nothing happens for 2.6 seconds. And 2.6 seconds, I don't know how drunk you have to be to make that feel smooth. But all right, maybe before the first coffee or something, you basically click and go like, did I click? I don't know. Oh yeah, I clicked. Oh, that's fine then. So yeah, that's a lot of operations, and we do them on the main thread. That's not perfect, is it? So how about we actually, do a separate thread? Silly man, JavaScript doesn't have any threads. Use C++ already. Actually, no, we have threads. They're called web workers. And what web workers are is basically the API looks like this. We take a script, a separate script. We create a worker from that, which means it runs in a separate thread in the browser. And then we can use messages. We can send data to our thread, and it can send data back to us. So instead of just blocking the entire UI, blocking the main frame, what we could do is we could start a worker, throw all the pixels to the worker, and then just do our own business. Oh, the click, great, so I'm gonna, update the UI, cool. And at some point, the worker is gonna send a message back after 2.6 seconds, hopefully. It's gonna send a message back with the actual output data, and then we take that data and draw it, and that's all. So the main thread is basically then not being bothered anymore. Also, if you wonder what the hell this syntax is like, okay, yes, great. So you have the data, and then you have an array with the data. This is called a transfer list. So imagine that. JavaScript, or if you write JavaScript, you can assume that there's no concurrency, right? Because concurrency can be really, really dangerous. Who here has worked with threads before? Who here has run into race conditions at least once in their career? I love how people actually raise their hands that have never worked with threads. How does that work? But okay, I'm fine. So basically what happens is when you have multiple threads running in parallel, and they access the same data at the same moment. One is writing, one is reading. It's very hard to tell what the program output will be, because you don't know in which particular order that happens, unless you take precautions. So basically, if you have one thread that writes a value and the other thread that reads a value, you don't know if it reads the value before the other one has written or after the other one has written, or even if they access it at the same time. In certain circumstances, the output will be garbage. That's not really cool. There's ways around that. There's semaphores, there's locks, there's all this kind of stuff, but JavaScript doesn't have them because we don't have concurrency, really. We have asynchronicity. That's a different thing. It's not concurrency. We can run multiple things in the background in this more or less the same time, and then they come back in a random order depending on how far they were, how fast they were. But we can't really access the same data at the same time as in threads doing that. So instead, we have to actually copy the data over. And what happens normally when we just would use post message pixels bracket and leave the last bit out, what would happen would be that it takes the data, copies it, and uses the copy in the thread. That might be great, but however, we are copying 4,000 by 4,000 pixels with 4 color channels each. So that's 4 bytes, that's like, I don't know, fuck tons of bytes. So that's actually really bad, and even worse so, you might think, okay, well then I use twice as much the memory. No, actually you're not. What happens is, the browser takes the original data. So let's say we have 10 megabytes of data in the image. So we have 10 megabytes. The browser takes the 10 megabytes and serializes them in a way that it can be actually copied over. So that takes 10 more megabytes. So now we have 20 megabytes. It moves that over to the thread that deserializes it, and then it takes another 10 megabytes. So we are now at a whopping 30 megabytes for nothing, right? So unless we want to do that and waste all that memory, or even if our messages are very small, it doesn't matter so much. But in this case, our messages are pretty large because it's all the pixel data. So what we can do instead is we can say, well, you know, actually, the main thread doesn't really access this data anymore. It just takes it to transfer it over. So we can actually do that. So instead, what we're doing by saying it in the array, saying that we want to have pixels transferred, what we are saying is, I don't need this anymore. I don't want to know the reason why, which is lyrics, by the way. I don't want to do this anymore. So basically what happens is we say, take this and go be merry with it. So that means that it actually, instead of copying, it removes it from the main thread and just links it to the new thread. And then there it is, no copying, no overhead. And we do the same thing when we send it back as well, and then we are good. So that's called transfers, or transferable objects. And this is how our thread looks. It doesn't come out as on the Beamer as nicely, but basically here the main thread stops being busy. So here is what happens. We parse our HTML, we parse the JavaScript, we start the worker. The green bit is where we render the image the first time, and then some JavaScript runs to actually get the data out, and then put that into the worker and start the worker. And then this is basically shaded, because here the web worker runs. So this is where the separate thread is running, and the main thread has nothing to do. It's free to do everything that it needs to do. And this is how we can actually see that in the browser dev tools. If you look at it, there's a main thread here, and then there's a dedicated worker thread here. And you can see that edge detection happens down here for the dedicated worker thread. And you see that there's nothing up here. There's a huge chasm of nothing. And that's what I want to be that's what I want my main thread to do, nothing, right? Because if I block it, then, well, right? Drunkard experience. So there's a few other things that you can do with web workers. There's a proposal for single input, single instruction, multiple data. That is nice because you can then basically offload it to a you don't really have to use that with a worker, but it's nice in a worker. You can basically say, you know what, I want all these pixels to do the same thing. So it's one instruction really, but it's a lot of data. And then it can actually use CPU features to make that happen if the browser supports it. It's not really polyfillable though. Another thing is, instead of having to transfer data around, can't we have a shared array buffer, which is a new proposal upcoming in ES 2017, I hope. Where's Axel when I need him? 2017? Yes, because a couple of weeks ago it was actually only proposal, and now it's final stage, right? Yeah, wonderful. So it's coming in 2017. Woo! It's behind flags in dev or nightly builds of the browsers right now, and you can play around with it. What it does is basically it does give you memory that can be accessed by multiple threads with all the risk associated, so you can actually run into interesting problems, and you go, what? So for instance, there's this hilarious problem. You write and read, like one thread writes, the other one reads from a shared memory array buffer, and it works great. And you're like, I'm done here, this is nice. And then you do that 1,000,000 times, and then the optimizing compiler comes in. Now the optimizing compiler can't know about this thread dependency because we haven't told him, right? There's this one program and there's this other program and they both do their thing, so I can optimize them. And then it optimizes them in a way, if you're unlucky, in a way that makes absolute sense for single-threaded programs. It's really efficient, but unfortunately it breaks the way that you access the memory, and then you actually get weird results, and you're like, so part of the proposal is also something called atomic that allow you to synchronize things. So you can basically say, wait, hey browser, please wait until, you know, this thing has happened, and then in the other thread you say this thing has happened, and then you can synchronize that this way. You might run into deadlocks. Good luck with that. Just, you know, take care when you do that. Another thing is there is plans to give you access, straight access to the canvas, because we have seen here there's quite a bit of JavaScript still running on the main thread. Wouldn't it be nice to just kick that off? As it turns out, 90% of that JavaScript is actually getting the pixel data from the canvas and, you know, transforming it for the worker. So it would be nice to have that in the worker itself. So we could basically just say like, yeah, there's a canvas, there's an image. This is the image. Load the image and put it onto the canvas and do all that in the worker. That would be nice, but it's not there yet. There's another thing called shared workers that has been around for a while. You can also theoretically have one worker resident, and if you have multiple tabs for some reason, for some applications you might need that, you can access the same worker from all these tabs, because as long as they're in the same origin, you are good. You can access your worker and you don't have to run another worker. So if you have 10 tabs, for some reason you have a weird application that opens 10 tabs and lets the user switch between them, very good user experience, then you can have a shared worker instead of having 10 workers starting. Very nice things. Have a look at them. The other thing is, so we're talking edge detection in images. Now, that sounds like a GPU problem, doesn't it? It kind of does, doesn't it? Even though it is not a 3D problem, it is definitely a graphics problem. So can we use WebGL? Yeah, sure we can. So this is basically the shader version of the Sobel operator. I stole that from the internet. The Spite is a great guy and has Jaume Sanchez. If you're not following the Spite on Twitter, you're doing something wrong, because he has gorgeous demos and actually is a really, really clever person. I had beers with him in Amsterdam, and so we're cool. Anyway, so yeah, this is the shader version, and the difference between shaders and JavaScript is that shaders operate on pixels in parallel. So that is actually very nice, because we have a lot of pixels that we have to process. So we can actually do this in parallel then, instead of having one pixel and then the next pixel and so on and so forth. This is the other part of the code. I forgot that it's actually spanning 2 slides. Holy crap. Well, it's WebGL. It always spans at least 2 slides. And this is how it looks. So here we see it's the same JavaScript code, but there's no workers involved. And then there's nothing happening here. And if you want to see how that behaves in the browser, it looks like, oh right, I haven't even demoed, oh right, yeah, wait a minute. I actually forgot to demo the web workers, didn't I? Let me show you the web workers as well. As you can tell from the URL, this is all online already. So this is in a separate worker. Da-di-da-di-da-di-da. This is fun, isn't it? Actually, that's the Frauenkirche in Dresden. If you ever visit Dresden, go there. It's really nice. So yeah, okay, here we have it, and then I can click here. That's a bit weird, isn't it? It always shows the original image. That's because I have to draw the image to get the data off. I could theoretically use a separate canvas, but I can't be bothered. But you can, what you can see is that I can actually, you know, it is behaving the way that I might want it to behave, but it still takes freaking 2 seconds. I mean, it's still JavaScript. We're not making it any okay, thank you very much. We are not making it any faster by offloading it. We make sure that our UI does not block. We can still use the application. It still responds, but it's not getting any faster, right? So it takes at least 2.6 seconds still to process this. 21, 22, 23. Yeah, okay, 2.6 seconds might be right. We could theoretically also be clever and then kind of like cut up the image into smaller images and then start multiple workers. However, as this application is clearly CPU bound, which means it does all the computations in a big loop, basically, right? So it's taking up all the CPU. It only scales with the number of cores. So if you have a computer that has 2 cores, 2 workers will do fine. But if you have 4 workers, they will not, because basically 2 workers will start, hog up the CPU, the third and fourth worker will be there, but not be able to do anything, because the first 2 actually take up the CPU already. And only when they finish, you get the other 2. So basically it doesn't scale indefinitely. It only scales with the number of cores, but it does scale with the number of cores. That's pretty good as well. Node.js people know what I mean. Yeah, so yeah, we can then play around with it and bask in the glory of web workers. But more interestingly, we can also do the same thing in WebGL. Let's have a look at how that goes. So let's see how we're doing here. Let me click here. Oh, look at that. Oh yeah, actually it's very, the drawing doesn't work properly on this computer, but basically relatively smooth, isn't it? And where's my mouse cursor? Okay, here. So I have to go there. Смотрите, пожалуйста. Спасибо. Смотри, пожалуйста? Не знаю. Я не говорю по-русски. So and what we see here is basically the main thread does a bit of, the green boxes always mean it's painting. We've seen that it has to still paint the image once, but then after it does that, after it does that, it does nothing again. It's basically done here again. But what we see is that the GPU does have a bit of work here. Obviously my shader is not very optimized. We could even make it better, but even a bad shader does work relatively well. Actually, it's not a bad shader, it's just I fucked things up, but that's a different story. Now, okay, that was not very impressive when it comes to general problems, right? Because obviously this was a graphics problem, so we solved it with graphics. Tall, wonderful, amazing. That doesn't really help if you have a non-graphics problem, right? Well, it does, as it turns out. As long as you have a lot of operations that can be run in parallel, and you can express them as numbers, you're basically good. You can't do things like hashing, because most hashing functions need certain things that WebGL does not allow you to do in shaders yet. It's not gonna come ever probably, but you know, right now it's not there. Because there's something called the compute shader that can do things like hashing and all that kind of stuff. But they're not in WebGL yet, they're not in WebGL 2. They might come later, but there's certain security considerations that need to be taken into account, because you don't want someone to mine bitcoins while you are on a website. Well, maybe you do, because you might be the programmer that gets the money from the bitcoins, but please don't. You can't, that's the good thing. But if you have certain operations such as parallel calculations, such as vector math, geometry math, or matrix multiplication, so you have a lot of instructions that can be run in parallel to compose a larger result, then you can basically use WebGL for that. Seth Samuel gave a great talk at JS Congress in that. By the way, JS Congress happens this year again in Munich. Highly recommend that. So basically, yeah, you get parallel calculations, but writing shaders is a bit tedious, right? It's a bit nasty to do that. There's a few libraries that actually wrap that away for you. There's Turbo.js that actually has a really nice syntax for you know, compiling a lot of things into shaders and then running them on the GPU for you automatically. It also has a fallback, so if someone has no WebGL available, then it uses JavaScript, makes it slower, but at least it works, right? And there's also GPU.js or something, so there's a few things that you can use instead of having to learn WebGL. Now, last but not least, who here has heard of WebAssembly? Who here has used it? That's how I feel when I have a problem with it and Google. It's quite fun. So WebAssembly is basically a possibility to run a binary, or it's a binary format that you can compile to from pretty much every language in the future. Right now it's C and C++. It is the evolution of ASM.js, which was a basically a subset kind of, a special kind of JavaScript, if you want, that was really was possible to actually optimize in a way that made it really fast. This is an actual binary format that uses a stack machine under the hood to execute basically native code, more or less. The difference between WebAssembly and things like Java or Flash is that they really design it. It's not working fully yet. It's a basically they have a minimum viable product right now, but they are working towards integrating it with the DOM and integrating it with JavaScript. So basically, you have a binary And you can call functions in it. So if you have a C++ program or a C program with a function multiply matrices, for instance, to do matrix multiplications, then you can literally call that function from JavaScript, which is nice. It makes it very transparent. You can also detect if it doesn't work. So if your browser does not support it, you can still fall back to WebGL or JavaScript or ASM.js if you think that's a good thing. So basically, it gives you a binary file. It hopefully in the future will integrate properly with a DOM, and you can cross-compile from pretty much everything later on, because right now the toolchain is built up to use LLVM from the Clang thing, and you can use mscript to then compile it. So basically, you go from your C++ program into this bytecode that is this intermediate bytecode, and then you can compile a ASM.js or WebAssembly from that. I would love to have used the logo. It doesn't have a official logo yet, so if you're interested in that, just go on their website, and they have, like, I think that you can still vote for the logos. I'm not sure, but it's quite fun. But there's a little bit of a problem, because you go like, ooh, WebAssembly, that's nice. You go to webassembly.org, and it has a getting started guide, and you're like, nice, this is really nice. And you run it, and then you compile it, and then you open the browser, and then you get that. Right. So WebAssembly is enabled without a flag in Firefox, or is it in Firefox? I'm not sure if Firefox does require a flag, but I don't think so. Chrome doesn't have a flag, and Edge I think has a flag, but also implements it. So you get a preview basically. But the problem is it's a binary format, and it has a version, because it's very, very early on, right? They're still developing it. Now they start to settle down. Now they have finalized what they think is version 1. And the interesting thing is, this here is the version number, and this here is the expected version number. So they basically went through the hexadecimal digits, right? The browser preview in stable Chrome requires version D of the specification. However, the toolchain produces version 1. Progressive enhancement? So yeah, no WebAssembly for you. I really wanted to demo it. I actually explicitly set up an AWS instance a couple of days ago, and it had a lot of issues, and then I reinstalled everything yesterday to make sure it's working with the latest version. Had a bug. You know, we are all been there. We really need developers on this, because we need to test these things out. So if no one of you has tried, please, I hope that when you go home later, you'll go like, I'll try WebAssembly just this one time to see if I have problems. And if you have problems, go to the IRC channel, go to the GitHub pages, open issues, submit pull requests. It's very easy to help, and it's very important to help, because this kind of stuff is really cool, but it evolves very quickly, so things may break, and we want a smooth developer experience. And that only happens if developers go, it breaks on my machine. And then people go like, oh, that's very interesting, and you know, let me guide you through. And then we fix it. That's how we do it. So don't be angry, don't be sad. It should work in most cases. It doesn't in mine. That's just, you know, that's my problem, really. Yeah, anyway. So basically it has an existing toolchain. It actually has 2 toolchains, theoretically. It is implemented in most browsers, and it's gonna come real soon. Please, please, please help make this work for everyone, because it's really interesting, really, really nice, and gives you good performance benefits that I can't show you because my toolchain broke. So to sum up, oh, I'm actually doing well on time today. First things first, if you block the main thread, that's a sad user experience. So sad, no. Using the main thread bigly, no. I have the best JavaScript. Anyway, so yeah, don't block the main thread, because you block the UI as well, and meaning the UI will stop responding to user input, and when it stops responding to user input, people may reload the page, see the same thing again, and then never come back ever. So you really do want to get off the main thread as much as you can. One way to do so is WebGL. This is a brilliant visualization from NVIDIA, together with the Mythbusters folks. You can see that basically the pixels, if you want to call them pixels, are generated in parallel. And that's the secret of WebGL and the GPU. GPU computing is heavily parallel. And WebAssembly is coming. We are not quite there yet, and we're still in the minimum viable product phase there. but there's great work happening, there's great work underway to make it very, very fast and very widely available. And the spec is settling down, so right now we shouldn't expect any big breaking changes anytime soon. Asterisk, bleeding edge means bleeding edge, because if if you're not careful, you cut yourself and you bleed a little. But generally speaking, that's what you want to try out. This is really, really good stuff. With that, get out of the main thread, use web workers. You can also use multiple web workers to make things more parallel, limited by the amount of cores that is, and it might actually not be limited by the amount of cores if you have an IO bound thing that you want to do in a worker, which you can also do. Because that gets you off the main thread, so it makes your application really, really fast and responsive to the user. What happens in the background is a different story. WebGL is very useful also for things that are not graphics problems, as long as they can be expressed as a series of instructions or a series of steps that can be run in parallel without heavy nesting or something like that, right? If you have dependencies between different things, a bit tricky, but as long as you basically have one value goes in, one value goes out, you're good. Or multiple values go in, one value goes out, that also works. And it's really fast. And then we have WebAssembly. Try that out. Your mileage might vary. Expect that to land anytime soon in other browsers as well. And experiment with it, try it out, report the problems that you find, and help us make that a great thing, okay? Help us make the browser great again. Browsers are already great. We don't have to make them great, so that's bullshit. But you get the point. Slides are already online. Sample code is online. You can try it out. Hop by my blog if you're interested in more stuff like that. If you're interested in the WebGL bits and pieces, my wonderful company is a great place to start, especially if you have architecture. If you have a floor plan of your house or office, you actually get the first 3D model in the browser for free, just saying. Hit me up on Twitter or ask me for questions. I'm around today and tomorrow. So if you have any questions, just come by and talk to me. Or we can actually take a few questions, I think. I'm not sure how the schedule looks. Thank you very much.
Thank you, Martin.
Wait, I've got this. Spasiba большое.
Gut gesagt.
Dankeschön. Vielen lieben Dank.
Okay, now we have a few minutes for questions. And
hi, Martin. Thank
Hi.
you for the talk.
Welcome.
So my question is about WebAssembly. So what is a reasonable fallback if there is one for WebAssembly? So obviously, if it doesn't work, you have issues, and what is the way to mitigate them? Thank you.
You're welcome. Great question. As I said, WebAssembly is basically the evolution of, or the successor of ASM.js. ASM.js should work in pretty much all browsers-ish, and there might even be polyfill. I'm not even sure if you need a polyfill. So you can fall back to ASM.js. The good thing, or the interesting thing is, that's very easy to do, because of part of the compilation process is you have your C++ or Java, C++, you compile that in the very first step into ASM.js, and then from ASM.js into WebAssembly. So you always have both anyway. So what you can do is you can see and try to load the WebAssembly. If that doesn't work, you fall back to ASM.js. If that for some reason doesn't work, might happen, might not be available on the network or something, then you can still fall back to WebGL if that doesn't work because it's a problem that doesn't fit WebGL, or if it's something that is not available in the browser because someone uses an Internet Explorer 6 on his Potato. That's fine, the web is diverse, that's great, that's actually one of the strengths. If you go like, oh, people are using old browsers, that's a good thing, they can still use old browsers. Make sure that your stuff works in old browsers, goddammit. Anyway, and then you can fall back to web workers, for instance. If that doesn't work, then you just run it on the main thread and go, pfft. That's all you can do. You're welcome. Listoshkin.
Hi.
Hi.
Hello again. So, question about like main thread blocking. Can I use, if it's Internet Explorer 6 and there are no iframes or no web workers, can I use iframes
You
to
can
unblock the main thread?
I'm not sure if it unblocks. That's actually a very good question. If you find that out, send me the results.
But I kind of
come
want
on.
you to find out before the next talk.
So here's the thing. I know that someone is using iframes in a trading application because it's It's a bank, and don't laugh at me. This is a true story. It's a bank, and for security reasons, they're using IE7. Just let that sink in, okay? I expected a groan like, oh man. So for security reasons, they use an IE7, and they use 2 iframes to basically mirror WebSockets. So one iframe is the receiving end, and the other one is the sending end, and they use post message for that. And I don't think it blocks the main thread because they also paint their UI at the same time. So I think it is a separate thread, but I'm not sure. I'm going to check that out, and I'm going to tweet about it and complain that you asked the question. One more?
Yeah.
Hey Martin.
Hi.
What about JSON parse on web workers? JSON API, a lot of objects. As I know, web workers work well with arrays, not objects.
That's
And
correct.
it takes a lot of data to copy to memory.
That's correct.
Any cases to solve this problem?
Don't use JSON. No, seriously, so here's the thing. If your JSON is relatively small and parsing is not an issue, then serialization and deserialization of JSON is also not an issue. Then you can do the copying thing and you'll relatively be fine. For instance, we have a 3D format that consists of a few hundred kilobytes of JSON. That works pretty well even on mobile, and we're good. If you hit a problem with JSON parsing being a bottleneck, you should switch to binary formats. There's protocol buffers, there's other things that I forgot, or you can just use your own format basically to use array buffers, because array buffers give you the advantage of being able to transfer them, so you don't have to have this overhead of serializing and deserializing them again. Also keep in mind that if you deserialize an object and use structured cloning, which is the mechanism that the browser uses internally, that might actually be relatively fast, speaking like it's fast, probably faster than JSON parsing itself, because the structured clone algorithm is relatively optimized. So probably it's not a problem. If it becomes a problem, don't use JSON, because JSON is actually a very tricky format to serialize and deserialize correctly.
Thank you.
Welcome.
Hello.
Oh,
May I ask a question?
da,
Yeah.
конечно.
So I heard somewhere that you are contributing to the specifications.
Yes.
Yeah, that's good. So my question is that, don't you see that JavaScript is approaches to the those C++ languages, and is that good that we are obtaining that shared array buffers and something like this? So eventually we will have C++ in browser. So and we will have to learn 2 languages. Is that good?
It's an interesting question. I don't think. Okay, if I have posed it as JavaScript in the browser, that was the wrong impression. That's something that I didn't want to convey. We're not going to have C++ in the browser. It's not going to happen. What we will have, what we already have, if you think about it, who here is using some sort of transpiler? Because you're using TypeScript or CoffeeScript or ES 2016, ES 2017, because it's a lot of people using a transpiler already. So technically, we already have multiple languages. It's language versions, but if you look at ES5 code and ES6 code, there's quite a bit of a difference in there, right? So we already transpile something. So we are already having the situation where we have a disconnect between what is actually running in the browser versus what you have actually written. Now, I wouldn't say that it's the same thing with C++, but I do think if used responsibly, I wouldn't write an entire web application in C++ and then transpile that into JavaScript. That's just asking for trouble, in my opinion. This is also the approach that more or less Unity uses a slightly different approach. For Unity, they also cross-compile into WebAssembly if you want. I believe what it gives us is the possibility to have code and libraries from very performance-oriented languages in a safe way in the browser and be able to integrate with them. It's not, as I said, Java and Flash failed because they were black boxes, sheltered away, and you had the binary, and then it's like, well, you have the binary, deal with it. But here we actually get a JavaScript object that we can call to, and it behaves more or less like a JavaScript object, even though it is not a JavaScript object. Fun fact, most of your JavaScript objects or functions are not JavaScript objects or functions because the optimizing compiler also turns them into native code. So you just skip the just-in-time compilation and directly go to the optimization, optimizing compilation. So I don't think it's a bad thing, and I don't think it's going to be C++ in the browser. If you can do that, I don't think you will be successful if you do that, if that answers the question. So yeah, for performance critical bits and pieces, it's great because you have a JavaScript bit that is very high, very fast, as it's pre-optimized. That is it.
Okay, we have time for one question, maybe?
Maybe.
Maybe. One good question. Any questions?
On.
Okay.
Он хочу
Хочет.
хочет.
Conjugation.
Ёлки-палки. Я не знаю. Abort mission. He wants to ask a question.
I'm using WebGL on my work every day, and you can use GPU calculations without WebGL 2.0
Yeah.
in WebGL 1
Yeah.
using extension. It's called float textures. You
Yes.
can load binary data to textures
Yes.
and use it. It's okay.
Yeah, it's okay, but I have never seen how the if the extension is widespread or not. I don't know.
92%
Oh, really?
on our. We have three. We have many players of our games.
One too many. Nice. Okay.
Really, millions players every week, and 92% of our players
Nice.
have this extension.
Okay. I didn't want to go into extensions because I thought you might
I
be
can
unlucky.
show you statistics.
That'd be interesting. Thank you very much.
Okay, thank you for great questions. Thank you, Martin, once again.
Thank you very much. See you around.
See you around. See you next year.